We're going to talk about magic squares of squares. So first thing we're going to do is talk about what a magic square is.
Now, I had not seen this video before I reacted to it because I'm a purist. Now, at this point, I was thinking this again. I was thinking classic. Classic. See? And it's the standard. This is the standard magic square that you start with. Like they say, it's a historic magic square going way back. It's fine. You know, it's the playing Wonderwall of magic squares.
7 plus 8 is 15, and then if you
and I'm more of a
diagonal,
Blur fan.
6 is 10 plus 5 is 15. So everything adds up to 15. So columns, rows, and the two diagonals add up to 15. That's a perfect pure magic square. In fact, this is the earliest, or up to some sort of rearrangement of the numbers. It's the earliest known recorded magic square. It's usually called the Lo Shu. There's records of it from about 2200 BC. The Chinese tradition has it that the emperor
old school.
Saw this magic square on the back of a turtle. It's a sort of beautiful story.
I know there are lots of other magic squares. We're going to talk about them shortly.
Yeah.
Is a magic square still a magic square if any number is repeated, or is that kind of imperfect?
Now, that facial expression there, that's me knowing where Brady's going with this.
That's kind
controversial statement. Yeah, it is controversial.
If you allow repetitions, you can really find magic squares quite easily, right? I could just repeat all the numbers here, right?
Quite easily.
Your favorite number, mine is 19. I think it would be 9, but
no, I did know that this was going to be a video about magic squares of squares. So I knew when Brady was saying things like that, I was like, I know where he's going with this.
Magic square. It feels like a fake magic square.
Fake magic square.
Look at 3x3 magic squares, but I want to impose one more condition, which is that I want the entries themselves to be the squares of numbers. So I'm going to draw for you an example of this, and it'll be a bit of a cheat. People
what a new concept.
Numberphile videos for a while are going to recognize this. So this is 29 squared, 1 squared, 47 squared, 41 squared, 37.
Oh, this video is just picked up immensely.
23 squared, 41
Look at it.
Squared, and 29. And
glorious.
This is a very famous
very famous
square, and it was made famous by Numberphile. So this is the Parker square.
Yeah.
You know what this video is
I'm
called?
calling out for crying out loud.
Yep.
This was famously Matt's attempt at old squares.
That's right.
Back when I had
it's
hair.
A very good attempt. I
I did. The hair fell out because of the Parker square. It was the shock. Almost.
Square of squares, right? So every single entry is a square number, right? And it's true that if you add up all the rows and all the columns, and if you add up the two diagonals, it all adds up to the same number. So it's not
I could have got away with it if Brady hadn't pointed this out. See, look, honestly.
Can we check that?
This diagonal here.
Going to the replay.
That's enough. Doesn't work.
One of the diagonals does not. And so in that sense, it's not quite a magic square of squares. It's what people tend to call a semi-magic square. And there's some repetitions of the entries. So for example, you see the two ones here, you see a couple.
Yes, I had a glass there I almost drank from. It's very important if you're filming with a green screen to make sure all the bowls and glasses are transparent. That just makes the edit so much easier.
Math, when you can't solve a really difficult problem, you try to solve a simpler problem. And making some of these.
That's very true. Very, very true.
The same as a way of
I allowed them.
simplify the problem and in a way that might use some interesting mathematics as well.
Okay, Parker square.
Great.
Good attempt.
Yes. Okay. So there are a couple of other squares that I want to show you because so as we saw in the Parker square, there's just a couple of things that aren't quite right. And there are some really famous ones. These are sort of from the late 90s. So one of them is called the Bremner square. Okay, this is a big one. Okay, so this is another attempt at a magic square of squares, and it's very good in sort of a different way from the Parker.
It's fine.
This
It's
time
fine.
you'll notice almost immediately
Very
there's
90s.
two entries that are not squares. That's where this fails.
I think that's a film quote. Very 90s.
Yes.
It was the 90s.
Not really. I don't think it is a little bit sad that they're not really squares. But what is true here though is that the columns and the rows and both diagonals add up to the same thing. So somehow we managed to at least preserve that property, but then we broke the squares. We do have distinct entries. So you know, you
Something.
feel like you're making progress. I mean, it'd be, you know, cool to have one that had like 8 squares, you know, and maybe only one that's not a square. I don't know of one, and I'm not sure if one has been found yet. There's another square consisting of square entries, which is almost a magic square. It's a semi-magic square. It's by Sallows, and in a sense, it's
Matt reacting looks pretty impressed. It's an impressed reaction.
However, just like with the Parker square, one of
Improvement.
the diagonals doesn't add up to the same number that the
Yeah,
other
I know how they feel.
add up to.
That feels like one of the best attempts so far, doesn't it? Like,
That's right. Yes. In fact, it's really nice that if you just remove one of the conditions, then you really can find them. It's a very difficult problem precisely because of how all of the conditions come together.
Yeah.
Very difficult
Difficult
problem.
problem.
question here: does one exist? Has anyone ever found a magic square of squares?
As far as I know, no. It's really sad. And in fact, what I want to do today is try to convince you that there probably isn't one. Okay. So I know that's sort of a sad thing to say. I would love it for it to be a magic
That is Matt's shocked face.
but I think sort of
Aghast.
geometry is giving us a bunch of
Mouth agape.
evidence that this just might not be the case.
They'd
So,
better
in fact,
back that up.
What geometry suggests is that if
see?
there's a magic square of squares,
Reacting Matt is open to.
This is going to be good.
You know what? I need
some
some
popcorn for this.
we can do.
Can I get some popcorn, anyone? Yeah, you can have my popcorn. That's fine. There you go.
Thanks.
Here we go.
Oh my God, yes. Thank you
All
for
right.
that question. Yeah. Let me try to show you where the geometry at least starts coming up. Let's do it. So we're trying to find 9 numbers, each of them a square. And so I need to give them names. I'll call them x1 squared and x2 squared,
It's one of my favorite bits of mathematics where
squared, and so on.
the temptation is to use different
What we're
letters
hoping
if you need
for
a bunch of
is
variables.
9
Mathematicians use the
positive
same variable and they
x1
just
to
pop
x9
a subscript underneath it.
that I can put into one of these 3x3 grids in such a way that the rows, the columns, and the 2 diagonals add up to the same number. And so I can actually write out what those conditions are in terms of just algebra. Right?
Like a big monster equation. or-
Yeah, it's going to be a set of monster equations, in fact. So let me show you. So for example, I need to know that the first row is equal to the sum of the elements of the first row is equal to the sum of the elements in the second row. So I can just write out this monster
Classic.
equation. Okay. I also need the same two
Already a
sums
monster.
to equal the sum of the third row. So I can write another equal sign here. This all has to be the same. Okay. I also need to know that this sum is the same as the sum of the 2 diagonals. So let me do those next. So there's x1 squared plus x5 squared plus x9 squared.
Yeah, fun fact, the x's are actually the monster's equation, not the monster itself.
Squared. This is a bit messy, but we still have to do the columns. So the first column will be x1 squared plus x4 squared plus x7 squared. Okay, and then I'll do the second column.
I know.
X squared
Watch Matt react here
squared plus x8
when it's
squared.
pointed out you don't need the last column.
But here's
A
something
lot of
really
people have sent me
really
emails. Oh, that is true. That start
all 3 rows
with
add up to the
that
same
setup
number.
in geometry.
And the first
Oh, so Matt's
So many
reacting,
emails. That just
talking
like,
about
oh, you can
the
do some equations.
emails
the same number.
that are sent in because of the Parker Square. But at the same time, did you see that? Reacting Matt was still listening to what was happening in the video
Going somewhere.
that Matt was reacting to.
But all the other ones that we have imposed. So
And he's
this is
able
sort
to
of an
respond and
important
understand
it cuts
that little bit of the proof, which I feel like we skipped over.
So there's only
It's
1, 2,
saying
3, 4, 5,
if you
6
know each of the rows add to a certain sum, the same sum, and you've constrained 2 of the columns, you've
Okay, so we have a
used
map
up
here.
bits from the rows, so the leftover ones,
System.
because if you add them all together, you get 3 times the total. The leftover column
the other 2 columns.
must work as well, which is what Matt is
That it's gonna be
reaction
really
Matt's
difficult
explaining there.
to solve this particular
Ah,
system of equations
what a reactor.
with the extra requirements that all
That's
these
why we
other
call
are different.
him the reactant. No, wait. Is the video's the reactant?
To me, it already looks difficult. But
Not a
all right.
chemist.
Do you want more paper?
Sounds good. Yes, we have 9 variables and we have these 6 equations, and so I want to think of these 9 variables as like
I'm just going to react to Matt reacting about the emails there for a second. I do get a lot of emails that start by setting up the equations,
Algebra. I can just reply with this.
and then they
9-dimensional
work
space.
through the algebra a bit. And that's what, I guess, a naive viewing of this video contains. And like a lot of number file videos,
Okay, so
you can
that's
kind of
like it's
explain
a 9-dimensional space.
the easily understood bit of mathematics, but then there's always a bunch of hand waving like the really serious, difficult stuff that comes afterwards. And so a lot of people who email in have done that beginning bit, which I think is amazing, and you should do that. You should give it a go. But once you've set up those equations, these people have then done an incredible amount of extra work into the consequences and things we can then say about those. So I don't want to be dismissive of people who send in equations like this and some algebra, not GeoGebra. I was thinking about surfaces. I think Reaction Matt says GeoGebra by accident. Send them in. I think it's amazing. But these folks have just gone above and beyond.
This is the Pythagorean relation. But, it's a different triangle, but this is going to be a 6, 8, 10 triangle. And there's something funny about this, which is that, okay, it's still true, so 6 squared.
Look how dismissive Reaction Matt is. It is the same triangle. It's just closer.
Wearing a disguise.
Yeah, wearing a disguise. Sneaking up on you.
Sense the triangles literally are different, but they don't feel like a genuinely different triangle. It looks like it just took the triangle I already
Similar.
and I scaled it up.
Similar is the
same thing
word
is going to happen
we're all thinking
with
of.
things like magic squares. It doesn't even have to be magic
The
squares.
video
Right? There's the
is
low
doing a
shoe,
great job of
and
not
so I
using
can just take
terminology.
the low shoe and just multiply
So you can
everything
see
by two.
they don't say rational point for a long time. They don't just say, oh, they're similar. They explain the logic and mathematics behind triangles being similar. So it's
Generate a
excellent square for any possible value.
4. Okay, and
I
now
think that was in
everything
my
adds up to
original
30 this time. But that's not very
extended
surprising.
number file
I just
video.
scaled every single number by 2.
from back in
So,
the hair
the
era.
equations that give you a magic square, it's just like multiplying those equations by 2. And so this doesn't really feel like a genuinely different magic square from the low shoe. In a literal sense, it is different, but somehow it sort of came from the same mold. And so that's really the important thing, is that when we look at all of these coordinates and I multiply them by 7, when I look at my magic square of squares, each one of these entries will get multiplied by 49 because 7 squared is 49. And so every single entry will get multiplied by 49. And then it'll still be true that the rows and the columns and the 2 diagonals will add up to.
I actually didn't find the Parker square using those equations. I feel like we're this deep into the reaction video to the reaction video. And if you're watching this, you genuinely care. I don't mind saying this. I just sorted square numbers into triples and then categorized them by what their sum was. And then I waited till I had enough triples with all with the same sum to then see how many ways I can arrange them. And then just check the other bits worked, which was grossly inefficient code. That's kind of my thing. That's my thing.
At an equation like this, x squared plus y squared equals 1.
I don't know if I mentioned it, but I actually wrote the code to find other magic squares for a live show I was doing. It's in the Festival of the Spoken Nerd show, just for graphs. I generate a 100 by 100 magic square based on values, like a number given to me by the audience. And it's got extra properties within it, like if you color in the numbers different ways, you get a picture of a smiley face. And I wrote the code to find that magic square, at least the base one that I adapted live on stage. And I thought, you know what else can I do with this? And I applied it to the square of squares problem.
8-dimensional space. So I don't know how to draw that here, but the object is out there and it exists.
So not only is that impossible
Now,
to imagine the playing field,
I think Reaction Matt,
don't even know what the
once Brady gets through this sport example,
That's right. Yes. So we really
Brady
have to sort of use
There we are.
our
trying to sneak some
imagination and the
sport
algebra. This is sort of a
into
really
the video.
important idea that we're
he does that. That's some good reacting.
But when we can't visualize things, sometimes the algebra is still there, and we can.
Now, Reaction Matt's thinking about that concept
So
of
we have this
a mathematical object
space. I think
being
it's
real
worth
and
reflecting.
existing,
Look back
ignoring
at the
Brady's sport thing.
equations that we wrote.
It's a real shape. That shape exists.
And so
Doesn't matter that
each
we
one of these
can't
equal signs
perceive it or imagine it. It's out
constraint
there.
on this 8-dimensional space.
It's one of my favorite concepts in mathematics.
And
Try
then I
and
put a
hunt it down.
constraint in it.
So
And
good.
so now what I'm holding is probably a 7-dimensional.
It doesn't look like that.
And then I put another constraint.
It's a good visualization of the concept of what it might, the idea of this thing existing and being a
If I have
surface.
6
It's a good
constraints,
representation of the
well,
concept.
okay, I'm just
Good reaction.
right. 8 minus 6 is equal to 2. Once I sort of put all these constraints together, it looks like what I should have is some kind of surface, some kind of 2 dimensions.
Always a surface.
Each constraint
Always a
cutting me
manifold.
down in 1 dimension. I started with 8 degrees of freedom, and I've taken away 6. And so even though it's very hard to actually visualize something like this, it looks like it could be some kind of surface.
So there's some two-dimensional surface that would hold the key to it.
There's some great popcorn eating. Holding the bowl so it's not got any of the green screen behind it, and then picking the right times to eat it, making sure I'm back from the mic a bit. Good work.
Is going to have coordinates x1, x2, all the way to x9. And this point encodes one of these magic squares of squares. Now what's important,
Has this surface got a name?
This is the big
Can
moment.
I suggest one?
what would you like to call it?
The Parker surface.
Watch the face. Oh, the popcorn.
That's awesome.
Popcorn drop.
All right.
Great reaction.
Okay,
That's
let's call it the
reacting.
Parker
Awesome.
surface. Yeah, so any point on the Parker surface is going to give you a magic square of
Yeah.
squares. Now,
It's never
the
gonna
surface
die.
Really is there. I think one of the
This poor
things we
person's worked
realize
very
is
hard on
that
this.
these X's could also be
And Brady's
not just
bullying him into
we are looking for
naming it
we
the
want
Parker surface.
But
There is a genuine point there. I do feel a bit bad that serious mathematicians investigating anything near
I mean like pi or e,
magic squares of squares,
infinite decimal.
if they want to publicize it,
Those are
Brady and other people are going to make them call it the Parker thing. So I feel like I don't want to take someone else's credit, but I feel like naming things the Parker something in no way implies I was involved.
so what
It's taken on its own
our
a life of its own. So I don't. I feel a bit bad, but I don't feel like I'm taking credit.
And this is where things get tricky, because inside this space, right, you can actually.
It's just a shame people can't name these things. Can't be named after the people who find them.
For example, the lower
Always be the Parker thing.
maybe two of the coordinates are the same. That could definitely happen. And things like the Parker square, have the property that some of the entries are the same, and so
A handful.
a point that has to
3
be
of them.
either. And this is the tragedy that we seem to face, is that on this surface, every time we have a point that seems to give us a magic square of squares, these points tend to lie on these very special curves.
It's a
of the
tragedy.
surface, where you have conditions like,
It's like that
x1
song.
is equal to x2, or x3 is equal to minus x7, or something like this.
Because when you
I will
first
not be
talked about
reacting to the
surface,
song.
I thought maybe there'd be no points on the surface where all of them are integers, but there are some there. So
That's exactly right. And this, you hit on something really important, Brady, which is that this is what makes this
By
problem
accident. Okay, that's a bit mean. One of the things that makes Numberphile work is Brady is very good at asking just the right question at just the right time. They are a perfect audience advocate. Like Brady's good at asking a question that a lot of people watching the video are thinking, and is often a question that, or a clarification that the mathematician may not have thought of themselves. So, a long way to say, well done, Brady.
There's this area of math called Diophantine.
That's why it's called the Parker
that
surface.
tries to exactly solve
I have a
this
lot of good
problem,
points.
where you take a collection of polynomial equations, like the ones that define the magic square of squares, and they try to find integer solutions, or prove that there are no integer solutions other than sort of a few obvious ones that we see, but
Trivial
that we're
ones.
not really interested in. The same thing happens with
Again,
Fermat's
avoiding
theorem,
terminology is
which
really good.
really aggravating. Fermat's theorem has solutions, right? 0 to the n plus 1 to the n.
That's why
equals
it's
1 to
considered
n.
the easier problem.
So the Fermat equation.
Okay, that's enough.
What makes it
That's
really
enough popcorn for
difficult
now.
is to show that
You know what?
there
I might
are
have
no
some more though.
solutions other than the solutions that contain at least one zero. Okay, and that's a much more difficult problem. In math, we have all these this whole slew of techniques for showing that systems of equations have no integer solutions whatsoever. But that's not the case here. There are integer solutions. So what we're trying to do is to show that there aren't solutions other than
Fermat.
the ones that we actually see.
Parker.
And that's a much more difficult problem to solve.
Yeah.
you told me
We don't just want integer solutions. We're fussy about the integer solutions we
that
get.
one of these exists. What you have shown me so far
Yeah.
has made me more hopeful that one exists.
Yes,
Yeah.
I understand what you're. So why do I think that one might not exist? Okay, yeah, I guess I did. Yeah, I need
More
a
paper.
sheet of paper.
More
yeah,
paper. Take away my hope.
Okay, so I'm going to try to explain why I think that even though we have this huge surface worth of points, all of which actually give you a magic square of squares, there's just no point where all of the entries are integers and they're distinct. Why do these points even exist in the first
If we were
place?
less worried about
this is a
integers,
philosophical
this would be
point.
trivial.
It's, points that satisfy polynomial equations that are all integers are very, very rare. They're sort of almost accidents of nature. And this is sort of something really important to bear.
I'm just going to
in mind.
react
So we
briefly.
know
So
if
this
instead of
continues to be
circles,
considered a derivative work.
curves come in sort of three flavors from this sort of.
And that accident in nature is a
The first one is called
interesting
rational,
one.
and in fact, the circle that we were looking at before.
because sometimes when you get these solutions, you're like, did the universe intend that? Is that an accident? Did if you got enough problems you look at in mathematics, occasionally you got one where you just get a solution by accident. It's not because of some underlying incredible bit of logic. It's just like, whoops, one just, slipped through.
to some number t on the real number line, then I can do a little bit of analytic geometry and compute this thing. You'll see that it's 2t squared divided by t squared plus 1, and then t squared minus 1.
Now, reaction map may appear motionless,
This actually has to do with
but
memory and
they're marveling at the level of detail
what's important here
that is in this video.
like an integer or some rational number, then these
A lot of
expressions
YouTube
are also
videos would have skipped over
fractions more generally. There's heaps
giving
of
one
rational
example
numbers
of the
on wheel.
coordinates in
And
terms
so
of
I
t.
just pick some rational number
Not
t,
number 5.
and I do this construction, and it gives me a point on my curve that has a rational coordinate. So rational curves.
There
have
was.
this
The rational thing to do.
that the moment
It's subdued reacting, but it's there.
I need 1 point to get started. Then I can use that 1 point to construct lots and lots and lots of other points. Then there's elliptic curves. So elliptic curves sort of have this funny kind of shape, usually. They're defined by cubic polynomials. Elliptic curves have this incredible thing that you can add points on them. Okay, so if I take p and q, okay, this is not p plus q, but if I just sort of reflect it down, I can call this p plus q. And this sort of crazy little construction that I just did happens to actually sort of satisfy.
Now, see reaction map.
That's a whole thing.
It's getting a drink of water
I can move the
from a
parentheses back.
transparent
So
glass.
elliptic
Very
curves have
sorry.
this crazy property that you
The
can add
reason
points on them. And
they
the
did
reason
that
that's important is because
Is on the
it allows
glass.
you
This
to
is the
also create
drinkulator from
new
Maskia that
points.
James Grime
So
designed.
to have an
And you
old
can
point
do
and add it to
calculations
itself,
by
and
adding
then
points
create a new
on a
point
cubic.
and add that point to itself.
So by adding 2 points on a cubic,
So
on this
elliptic
side you
curves
get
have this-
addition.
also this property
On
that
this side you get
construct
multiplication
and
actually.
propagate.
And so you by
So
add you
rational
draw a
numbers
straight
and
line like
elliptic
you just saw in the
curves
diagram there. And so because this is such a similar situation, what was happening in the video, reaction Matt took a drink of water from the glass that uses the same
higher
length.
ranking
Is that
curves.
they always have finitely many points with.
That's how many
coordinates
different
that are
levels
This is a
reaction
spectacular
Matt is working
example
on
of the 80s.
at any point in time.
It was proved by Faltings, and he got the Fields Medal for this theorem. So this
A lot of
is
great things come from the early
It
80s.
was called the Mordell conjecture back then, and now it's Faltings theorem.
No, I know for a fact
Curve.
reaction Matt's
Okay, it is-
was born
it
in
is a subject, but I'm
1980.
telling you this story because it actually
Hence-
plays a very
hence the
key
joke.
role in our surface. So
From
when
the
we
early
have
80s.
Curves, they sort of come in 3 different flavors.
Very early
Two of
80s.
those flavors have
A
lots and lots of points,
as
and
a
one
zennial,
flavor does not.
if you will.
So what happens with the surface that we were calling the Parker
Look at that
surface
paper. Look at it.
is that as a consequence
That's
of
'cause
some
it's
work
its
that me
name.
and a couple of co-authors, Nels Brown and Jordan Thomas, were working on, is we managed to show that on this surface right here,
That was me chasing a
there are
fly
only finitely
that had
many
flown
curves
into the
of
studio.
two types. And this is
It's
really
incredibly
something
hot
that
here
surprised
in
us.
the UK at the moment, and we're actually
It's called
recording with the
curves.
window open. So if you heard any background noise, I
Exactly.
apologize.
You can take a surface
And
just like
there
chop
you
it
can
up
see
into lots
Matt
of
was
pieces.
reacting
And then,
to a
you know,
fly
if you're looking for
that was
points
buzzing
on
nearby.
that give you a magic square
Reaction
curve,
Matt
one thing you
reacts
might try
to
do is, instead of
anything.
looking at the whole surface,
Then they're not, you know,
that surface.
biased.
And maybe you get
and what
lucky,
they
maybe
react
your
to,
curve is one of these two
Something
types.
happens, there's
And
stimulus,
you can
boom.
use what we know
Reaction.
about these two types to actually construct magic
See,
square
this
square.
this is
But
the
sad
mathematics
thing
you got to
is
do.
that
For everyone who just
the
emails me with the
surface,
equations
the
and a bunch of
parameterized magic squares and
GeoGebra,
squares, the Parker
sorry,
surface,
algebra
has
and geometry.
only finitely many.
Not GeoGebra.
No, you
That's
need
a
to
bit of software.
actually.
It doesn't only need one.
Investigate it
It
and
only
discover
needs one.
things.
You're right, but here's the crazy thing is, it has more than one. In fact, this Parker surface has 368 of these curves that we know of. So there's at least
At least.
368 of these rational or elliptic curves. The sad thing, though, is that the way we've constructed these
You could have one a day for a year. You could have a calendar.
slices like this, you know,
of
what
the rational
happens
curves.
If I take x1 equal to x2, that gives me some kind of curve on the surface.
Sorry.
And then either this curve,
elliptic curves.
or the curve itself might break into a few pieces when I do the slicing. Those individual curves are either rational or elliptic, but they have this property that x1 is equal to x2. So the 368 curves that we can find, they contain points, but all of the points on these curves are going to give us these kind of fake magic squares, which is really, really sad. Okay, and so here's the final kicker, though. There is a conjecture. So Parker surface.
Conjecture.
So this has finitely many rational and elliptic curves.
We're out in the wilds of conjecturing
Try
now.
to use these curves to produce points, it isn't looking so good. Like I say, this is some theorem that came out of work that me and a couple of co-authors were working on, and I mean it was kind of neat. I mean, we didn't expect that we would be able to prove something about this very specific surface. But now the kicker is that there's something called the Lang-Voida conjecture. This is the incredible thing. This surface that we have here is a particular kind of surface. It's also called the general type surface. And Lang and Voida sort of made a series of very deep conjectures. But when you apply those conjectures to the surface, what it says is that outside of the rational and the elliptic curves, there can be at most finitely many points on this surface.
Yeah, Matt, see that reaction?
Right. There's tons and tons of points on the surface.
Only
but
finitely many.
There's only going to be finitely many points outside of this nice locus of rational elliptic curves, all of whose coordinates are going to be integers. There's finitely many, I'll call them rational points outside the rational and elliptic curves. So where does that leave us?
I get the feeling from talking to you, as soon as a search space becomes finite, you become very despondent and lose hope.
Yes. It's finite because of this sort of general conjecture, but often finite can mean empty as well. And so it's entirely possible
That's a type of finite.
that it's
the
not
worst.
just finite, it's just isn't
The worst type of finite.
a set of points. So somehow the moral of this story is that either we need to find some more of these rational or
We do.
Elliptic curves.
That's not strictly true. The moral of the story is to give it a go.
I always hope for the best.
We can't just keep trying this all the time. And in fact, we might actually get a complete list at some point of all of these. And then, we really understand
One day.
points on rational and elliptic curves. So once we have that final list, we'll be able
The
to
finite list.
ascertain whether, you get one of these magic squares of squares, at least sort of from that point of view. Or the other hope is that, we do this and we find nothing, but somehow there's this miracle. And for some reason that we just don't understand, there's a couple, one or a few more sporadic points on the surface, all of whose coordinates are integers. But everything we know about
So unlikely.
surfaces and the geometry of curves is really pointing to the idea that
Never
there just
trust the
isn't
sporadic
a
points.
magic square of squares
Unreliable.
in the way that we would like it, with distinct integer.
I don't follow the rules. The maverick
I want to
points.
end on a good note, though, so
Oh, thank
I
goodness.
need one more piece of paper.
Okay.
So what I want to show you is something that's kind of mind-boggling. So we've been asking
You
for
can watch Matt process the joke.
Very funny title.
He's reacting. That was a
take
good
back
joke.
all
The sass I said about Brady.
that the columns, the rows, and the two diagonals.
Yeah, you
that
can
are-
see there's like a
really
half-life
interesting.
of reaction.
Okay, but now
So
we can
Matt,
do-
there, watch the dimples is gradually fading.
Broke here.
And so that previous reaction
You got a
has
4
like
by
a
4 now, and this is
taper
kind
off. Oh, new reaction.
Okay.
Psych back up
This
again.
is a 4x4 magic square of squares. This is not a fake magic square of squares. This is the real deal. Due to Euler around 1770, thereabouts. These magic squares of squares have a very long history. If you look here, sort of all the
I like
rows
the
of
way they
columns
described it
and
as
the two
fake.
diagonals add up
Like in the same way you'd buy a
to
fake
515.
Rolex
So this is kind of
on
crazy.
on
There's a
vacation.
4x4.
Hey, buddy,
There isn't a
So close.
want to buy a magic square?
And if you go on the internet, you'll also
Fake?
find a 5x5.
Who's to
and
say?
a genuine one,
What's
not a
real?
fake one, and if you
Very
dig hard,
philosophical,
there's also a 6x6. So,
On the
from
philosophical
geometry
market,
point
the
of
grey
view,
market
it's
they call
actually
it.
Not too surprising. In fact, I would actually think it'd be really cool to show that if you take an n by n grid, then and n is at least 4, then you can produce one of these magic squares of squares. And so
What happened when you kicked up? Because I thought if you applied that same process you just showed me
right.
to this, you'd have the same problem. You'd come up with a surface that was really constrained.
So I
Exactly.
picked the
Okay, so what
only
happened, right. So let me just sort of
dimension
explain briefly that, right. So if I have like
where
an n by
it's
n grid,
can't-
right, that
can't
means
be
that I'm
done.
gonna have something like
To be
what we
fair,
did
I deliberately
before.
picked a
So
3 by
this is
3
n entries this way
because that
and n
was
entries that way. Okay, so if you
the most
have an
open
n by n grid,
question.
you have n rows, you have n.
I mean,
columns.
extra background fun
You only have
fact.
2 diagonals,
Where was I?
but
Is it like
now
the University of Leeds somewhere?
tables do you have?
My wife Lucy was at like a conference. I had some time to fill, and I didn't have my laptop. So on my phone, I just looked up unsolved problems, looking for low-hanging ones I could do a video about. And I'd recently written
We're on an n by n
the code to find magic squares for the Festival Spoken Nerd Show. And when I saw there was this open problem specifically for the 3 by 3 magic square of squares, and at the time I saw like the search was already, people had checked numbers way bigger than I ever could. So I knew from the get-go I wasn't going to find a solution. But I still thought, because it'd be funny, how close can I get? And I had no idea just how entertaining that would end up being.
Plus 2 things that I need to set equal to each other.
So the Parker surface is no longer
It's
two-dimensional.
Exactly. It's no longer two-dimensional.
It's like a huge blob.
Exactly. It's like a huge blob, right? Right. We go up 1 dimension to n equals
A lot of Parker things are often described
4,
that way.
right? And now we're in 15 dimensions. We've made roughly 8 tuts. And so it's like a big blob. It's not a surface anymore.
Parker
And-
blob.
Yes.
The
that's
Parker
right,
blob.
Parker blob in n dimensions. And so the cool thing though is
The
that
n-dimensional
sort of
Parker
measures
blob.
that we have about points on these
That was my
blobs,
nickname in high
it's
school.
not a surface anymore. It's a much
Now,
bigger-
just to react to that reaction, the n-dimensional Parker blob, when I said that was my nickname in high school, that's a running joke that we have here filming at Stand Up Mass Enterprises. It's like a, that's my new band name substitute. And I think actually Alex, camera person, who is filming this, shout out to Alex. Yeah, they look pretty happy right now. I think, did you start the,
And so it's sort of not
that was my nickname in high school?
geometry that you would find a 4 by
One of us did. Oh, well. Someone here
or a 6 by 6.
at Sound Like Mass Limited Enterprises Studios started that joke, and it'll be very funny to deliver it to camera with Alex behind the camera.
And square, where there isn't a solution again.
Oh my god, that would be
What?
amazing.
Like
That
some,
would
by
be-
some
Nah.
freak curve.
Yes, that's right. And that could happen.
If you're
because-
thinking, did this video really need a whole camera person? You're thinking, well, there's some complex, real complex camera moves. I didn't want to hang this myself. I'm busy.
and no one has really sort of sat down to explore it. There's some really interesting mathematics.
It'll alarm you. We're kind of just, we're fitting this in the gaps of other, what do we call, like, more serious projects? I don't know if anything I do can be counted as a serious project, but this one, Brady's like, I got this funny idea. I'm like, that is a funny idea. I'll get onto it. So good. So anyway, that's why we're overstaffed. What we're doing.
Very famous theorem of Lagrange. In fact, Euler sent this particular square to Lagrange with no explanation about how he had constructed it.
Classic
And
Euler.
Lagrange had to kind of work hard, and then Euler eventually did publish the method, and then once Lagrange saw what Euler was doing, he was really able to complete his proof. But it's amazing to me that sort of this that might seem just like pure fun actually ends up having some really sort of deep and interesting consequences.
If you find all the finite curves on there, rational and
that's-
elliptic,
Yeah.
and they don't throw up what you need, can you prove that
And the
there are
finite other
those-
points.
Can you prove that there are none of those other points floating out there? Is that provable? Can you say, yeah, there aren't any points as well, or are they always going to be a bit of an unknown?
With current mathematical technology, I would not know how to do that, and I think that's sort of just in general, it would be
Right, the
great to
limits.
have some kind of mechanism to do.
That's where I exist. Beyond the frontier
Yeah.
of current mathematical knowledge.
Can I find this sort of hypothetical set of finite points,
Parker points.
the Parker points, if you want? Yes.
The Parker points. Now reacting to me reacting to what I'm going to have to react to in the future. And that's the end of that video. I'm going to wrap it up there. I know you're thinking, would it be funny if there were more of these? But I've only got a finite amount of patience, and Alex is doing the